Hello and welcome to the course Climate Hazards and Disaster Mitigation. Today we are going to discuss role of climate change in modulating future occurrences of climate hazards. What we learned last time, we understood the concept of big data and its key characteristics. We identified major big data sources used for climate variability and climate change analysis. We explored the role of big data and hydroinformatics in enhancing disaster mitigation. Today's learning objectives are: we'll appreciate climate related risks due to climate change and its role as a hazard multiplier. We'll learn how warming alters temperature and precipitation extremes and how these extremes influence climate hazards. We'll also recognize the role of early warning system and climate risk management in reducing future disaster risks. Climate change, just a quick wrap up because we have already discussed it earlier. So the long-term alterations in the average global weather patterns, which are primarily driven by the greenhouse gas emission from fossil fuels. As the global mean temperatures are increasing from the baseline, the weather is becoming more and more extreme. The indicators include increased temperature, altered rainfall, sea level rise, etc. So small mean shifts will increase the probability of extreme events, and even the sea level rises will amplify the coastal flood risks. So here's a comparison between climate risk in 1.5 degree versus 2 degree global warming scenarios. So if you see extreme weather, in 1.5 degrees there will be 100% increase in flood risk, but 170% increase in flood risk if there is a 2 degree global warming. Water availability, 350 million urban residents will be exposed to drought if a 1.5 degree warmer world we are living in. And in case of 2 degree warming, it is 410 million. Sea level rise, 46 million people will be impacted by sea level rise of 48 centimeter in 1.5 degree warming world. In 2 degree, it will be increasing to 49 million people, where the sea level rise will be 56 centimeter. When we talk about food, every half degree warming will consistently lead to lower yields and lower nutrition content in the tropical regions. And there are other impacts on the people, species and Arctic. If we talk about heat waves, 9% of the world's population, that is 700 million people, will be exposed to extreme heat waves at least once in 20 years when we have 1.5 degree warming. That increases to 28%, that is 2 billion people will have heat waves at least once in every 20 years. So you can see how this 0.5 degree just change in scenario is being modeled, and the effects are such disproportionate. So that means if the warming will be up to 2 degree levels, that would cause unprecedented changes in the climate, and of course it has multifaceted impacts on different sectors, particularly disasters. Talking about climate risks, so here we will be discussing few of the regions where the risk assessment have been done. So in one of the studies, it was noted that the Himalayan meltdown, that is number of glaciers in the Hindu Kush region, is rising. It may appear to be somewhat perplexed at the start, but the number of glaciers which have increases, this can be paradoxical because of the severe fragmentation. That means bigger glaciers are fragmenting into smaller glaciers. So the number is increasing, but the overall area is decreasing, and they are rapidly melting as well. Since 1950, only reduction in glacier area has been observed. Eastern Himalayas have tended to shrink faster than the glaciers in the central or western Himalayas. So in the western part of the Himalayas and central part, that is not that much, but the eastern part of the Himalayas, it is more accelerated warming. Faster snow and glacier melting due to warming is already manifesting in formation of glacial lakes. So we have GLOFs, that is glacial lake outburst floods. They are becoming more frequent and causing very significant damage to the local infrastructure. Most of the lakes at high altitude have reported a rise in water level of 0.2 meter per year, along with the surface areas expanding. So this glacial lakes outburst, that is a very big challenge in the Himalayan region, and that can lead to lot of problems. So you can see here many glaciers. What is a retreat in Zingzingbar glacier? It is 22 meter per year. That is a glacier retreat. Chota Sigri it is 6.5, Bada Sigri it is 30 meter per year, and then South Lonak Lake 42. Here is where the Sikkim disaster happened in the recent past. So that is why these conditions are very alarming. Talking about climate risks, so these are the places which are topping climate risk across the globe by 2040. So you can see particularly the Indian part, the water stress, flooding, wildfires, and in some parts heat stress to some extent. So, and as well sea level rise. So these are the predominant problems which India is going to face. In some places here you have hurricanes and typhoons, but majorly the flooding, wildfires and the water stress, these are the three climate risks India is likely to perceive. So you can see most of the regions, they are perceiving a variety of risk. It is not common that every region is facing a similar threat. So that makes this problem more complex. Discussing how climate change acts as a hazard multiplier. The climate change is increasingly affecting human security worldwide. Unpredictable rainfall and extreme weather events can trigger competition for food and water. Declining agriculture output can lead to loss of income for broader segment of people. Drought, floods and storm and sea level rise are already causing more than 20 million people to leave their homes and migrate to other countries. Thus, climate change is called as a threat multiplier because it intensifies the resource scarcity and worsens the existing socio-economic and environmental factors. So you can see that due to climate change, there will be more stronger hurricanes, droughts will be longer, there will be more probability of wildfires and higher flood risk. So the threats are multiplying. The rising frequency and intensity of flood, drought and storms and heat waves have increased globally since 1970s. Hydrometeorological disasters, they are on the rise. More and more population is exposed to these disasters and heat waves have become more frequent, hotter and longer in most of the land regions. So this is an image taken from what are the temperatures recorded on 30th April 2022 across India. So you can see most of the places were having temperatures in the range 38 to 42 degrees Celsius and even higher in certain regions. So you can see it's almost the entire belt. So large amount of people are exposed to these high temperatures. Talking about a very recent case, the IMDS forecasted that the conditions between April to June 2026 could be a mixture of warm nights throughout the country, where hotter than normal days, particularly in the eastern, northeastern and northernmost regions, will be accompanied by above normal duration of heat waves. So the warming will be on the rise, except they have forecasted that some parts of central India, there could be some exceptions. Otherwise, the nighttime or minimum temperatures will be on the rise. These elevated temperatures can lead to heat-related illness and additional stress on the infrastructure and resource management systems. We already saw earlier some 20 million people were forced to leave their homes. So that brings us to the problem of climate migration. Climate migration refers to the movement of individuals or communities which are compelled to leave their homes because the environmental conditions have changed or exacerbated by climate change. These environmental changes may include sudden onset disasters like hurricanes, floods or wildfires, as well as slow onset disasters like desertification, sea level rise and prolonged droughts. Unlike economic migrants who usually move out of their homes for more better job opportunities, the climate migrants are driven by direct or indirect threats of environmental degradation. So you can see around 1.6% of South Asian population was displaced due to climate change. Africa, that is 3.5% population. Latin America 1.6% population, and the figures are more alarming as we move towards the future. So there has to be certain mechanism where this climate refugees have to be tackled properly, and that can only happen if we make proper adaptation and mitigation strategies. Coming to the precipitation temperature scaling, as the global warming makes the temperature more riser, this warmer air will hold more vapor, and this higher atmospheric moisture content would increase the potential intensity of heavy precipitation. So a Clausius-Clapeyron relationship states that there will be 7% more water vapor holding capacity of the atmosphere per 1 degree rise in the air temperature. That means for shorter duration extremes, rainfall intensities will be much higher. Sometimes they can scale with or even exceed the Clausius-Clapeyron relationship if some local conditions are there which are exacerbating it. So you can see that natural climate without human influence, the warm moist air will rise, then clouds are formed, and then it will rain. Future climate with warmer air, for every 1 degree more warming, the clouds can hold 7% more water, and it will create more heavier rain, and this could lead to greater risk of flash flooding. Due to climate change, the global precipitation patterns are already altering. It will lead to more rainfall in some areas, and it will render other areas under water stress. So you can see that this inequality, if you particularly highlight the Indian region, you can see that some parts, particularly the southern peninsula part, will experience little bit positive change, while most part will experience decline in the rainfall intensity. Changes in temperature extremes. So the IPCC reports present several scenarios how temperature could shift, that there could be shifts in the seasonal maxima, that is the seasonal maxima could increase. The seasonal there can be scale shifts where the variability can increase, and there can be some shape shifts. Similarly in minima, again there can be location shift, that is the mean is shifting towards the left, then the variability shifts and the shape shift. So the future climate would experience more extreme weather, that is the shifts in the mean. The weather will be more variable, that is the shifts on either side, and the symmetry will be destroyed. So this kind of effects will be observed in the future. What about droughts? So in the regions where strong increase in drought magnitude, the events will show a very rapid increase in the drought occurrence with warming. More than 50% of the land could be exposed to a baseline 100-year drought event every 5 years if we go by 3 degree global warming. So they have simulated 1.5, 2 and 3 degree scenarios compared to the baseline scenarios and different projections. So if you can see 3 degree, India is almost painted in red, where you can see the magnitude increase is much higher. Tropical cyclones, there will be increase in the proportional of very intense tropical cyclones. Some studies have projected that there will be fewer cyclones, but those will be very intense. So the coastal flood risk will be amplified because of the increase in the cyclonic activity. Flood hazards. So flood intensity is projected to increase over most areas of the globe with very high uncertainty in some places. Around 75.9% land in the humid regions will show an increase in the flood intensity, while in semi-humid and semi-arid regions it will be close to 68 and 63%. So that much area of land will be prone to more flooding in different climatic regions. Coming to compound climate risk. So compound risk are when two or more climate hazards affect each other, which increases the overall severity. The climate hazards are usually characterized by single extreme events, multiple coincidences, sequential events that interact with the exposed systems or sectors. Now compound events can be of two types. They can either be of same type. When we talk about succession of that events, for example, one cyclone followed by another, one spell of extreme precipitation followed by another, so they become the same type. Or different types, like a landmass can be caused by biomass fire and which can be followed by intense flooding. So they are type of a cascading disaster, one after the another. So compound events, we have already seen that they can either take forms of concurrent or consecutive hazards, that is compound or cascading event. Now these events will have more negative impacts than their individual occurrences itself. So how this compound climate risks come into picture? For example, climate change, urbanization, other factors are changing risk. So there is due to warming, the heat wave risks will increase. So that will increase the demand of water and electricity. It will escalate the heat related issues. And if due to higher temperature there is more rainfall, that will cause floods, which will cause displacement of people, which will damage infrastructure, and all of these will affect the utility services, the physical and mental health of people, environment, it will be deteriorating, economic losses for sure, and strain on healthcare system. So the risks also compound when the hazards are also compounding. Early warning systems are one of the effective ways where we can handle such kind of climate risks. So if we can identify the upcoming hazards very early, the communities can be prepared in advance and the disruption can be minimized. There are 4 elements of an early warning system. The first one is disaster risk knowledge, knowing about the disasters. Second is detection, monitoring, analysis and forecasting. We can detect the disaster, we can forecast it much earlier. Third is dissemination and communication. Once the disaster severity is flagged, then it can be communicated to everyone so that if they have to be alert or evacuated, that decision can be taken place. And preparedness at all levels to respond. In case the severity is high, then we should be prepared with everything which will be required for evacuation measure. So all 4 elements are equally important. So early warning systems are an essential component of risk reduction strategies for climate and environmental hazards. The United Nations and WMO recognize the importance of EWS and have made efforts to develop them via the Early Warnings for All initiative under the UN Sendai framework. So the UN defines EWS as an integrated system of hazard monitoring, forecasting, prediction, disaster risk assessment, communication and preparedness activities, systems and processes that enables individuals, communities, governments, businesses and others to take timely actions to reduce the disaster risk in advance of a hazardous event. So that is what in a nutshell entire EWS is summarized. Now when we talk about weather related EWS, they operate on a warning chain which includes different things. So you have observation, you have weather forecast, you have hazard forecast, impact forecast, warning and decision. So these are the 6 components. Each components are connected by a bridge. So this is called the bridges of death. Why they are called bridges of death? So it is a metaphor which describes that if any of the 5 consecutive link fails, the entire system will fail. For example, from 1 to 2 you navigate, 2 to 3, but 3 to 4 if you are not able to navigate, the entire system would fail. That is why they are called bridges of death. So it is very important that we establish good EWS. Based on that, we can do some nature-based solutions to reduce the risk and also some engineered solution to improve the resilience. Synergies between adaptation and mitigation. So nature-based solution create an opportunity to increase carbon storage capacity while also contributing to reduce weather risk. Identifying these opportunities can help avoid trade-offs and develop mutually reinforcing policies. For example, you can look at 2 different lenses, whether I should mitigate or I should adapt. So both of them, both of these actions should be thought of. We should not rely only on mitigation, neither only on adaptation, because mitigation actions that increase exposure and vulnerability to climate change, while adaptation actions will undermine the mitigation effort. So at some place we have to make a trade-off between them, and we have to think under a particular situation which will be more better. So there can be something like at local scale, if you do more of a mitigation, global scale more of an adaptation, or global scale more of a mitigation, local scale adaptation, that has to be thought of. but at a local scale it is more of a mitigation and larger scale policy where the adaptation measures, for example reducing the carbon footprint globally, if everyone acts, then they can put into more better practice rather than at the local levels. Climate risk management. So despite several climate policies, the consequences of climate change impacts and the potential loss still pose a risk. Residual risk is a risk that remains after adaptation and risk reduction effort. So even if we do some adaptation and make efforts, there is some risk which is always left behind. So the idea of climate risk management is to provide mutually reinforcing steps, which is considering all the stakeholders across sectors and they participate in this formulation. So you should have all the aspects into picture and then take all stakeholders together to formulate a climate risk management plan. Also, there could be one paradigm shift where we can move from hazards to impacts. So far your ML models, they focus on hazard forecast, but they do not trickle down the early warning chain. So next step can be impact centric or impact based forecasting. So ML can leverage the previously unavailable predictors to produce better possible forecast. Approach is to use, let us say, weather forecast as predictors and an impact related quantity as a target. So let us say rainfall, temperature, these all parameters or some additional required can be taken as predictors, and impacts like, for example, how it will affect agriculture, how if it will affect the hydropower or any other sector. So that can be impact related targets. So the impact of weather extremes on vegetation status as observed from satellite imagery can be predicted by leveraging a vast archive of satellite products and aligning them with the historical weather data to create training images. So the central idea is that impact based forecasting would help in achieving the targets, and it will be more powerful than just hazard forecasting. So to summarize this lecture, what are the key takeaways? Climate change shifts baseline climate conditions leading to more frequent and intense extremes. Warming enhances heavy rainfall and flood risk while increases drought severity and duration in vulnerable areas. Compound and cascading hazards are emerging as major risk drivers under climate change and urbanization. Impact-based forecasting is a transformative approach in weather and climate science that shifts focus from what the weather will be. For example, if you say 100 mm of rain, that is what the weather will be, to what the weather will do. Example, this rain can flood 50 houses, disrupt power lines. So we should more shift on impact-based forecasting to improve upon our disaster mitigation efforts. One activity suggestion for you: how have climate risks changed or evolved in your regions? Are there any discernible impacts? Collect evidence based on literature. Here are some additional reference materials. Thank you for attention. In the next lecture, we'll discuss accounting non-stationarity modeling in climate hazards. Thank you.